All right, inertia, number one. What's inertia anyway? Well, inertia is a word basically that in our statement of Newton's first law, that objects like to keep doing what they're doing unless acted on by an unbalanced force. Inertia is kind of the word for that want, the things, the tendency that things have to keep doing what they're doing. That is their inertia. And the more mass those things have, the that larger that they are, the more inertia that they have, right? If you have like a giant truck, for example, versus like a very, very small car, that truck is going to want to keep doing what it's doing even more than the car because of its larger mass. So that's what that word means. So here, you might be wondering, like, hey, how come we're doing an assignment here without any notes? You should be able to figure out all the answers to the questions on this without any new material beyond what we know from from units 3 and 4. So, consider the velocity time graph of an object shown below. So this is a velocity time graph. So what's velocity for the first second? The velocity is 0, so it's just sitting there. And then from 1 to 2 seconds, the velocity changes from 0 to 3. So it's speeding up, and then it's cruising at 3 meters per second, and then it's slowing back down. Now, the trickiest thing that people, physics students, such as yourselves, look at this sometimes and think, okay, now it's going backwards. It's not going backwards, it's going forward. These are all positive velocities, but it's slowing down. It's going 3 meters per second, now it's only going 2 meters per second, now it's only going 1 meters per second, now it's going 0, and now it's stopped. So it could be, sometimes, I don't know if this has ever happened to you, when you're like coming into town, coming south on 11, and you're at the traffic light in front of Lowe's, and it's a red light. So that's how you can tell it's red, because that one's lit up. And there's your car, and you're sitting there. And then there's this other one that's like in front of the other Walmart entrance up by the Burger King there. And this turns green, and you're like speeding up. You're like, okay, cool, and then I'm speeding up, and then like just when you get halfway between them, this one turns red. So you cruise a little bit, and then you slow down again. So that's something like this. All right, during what time intervals is the object accelerating? So accelerating means the velocity is changing. It doesn't necessarily mean it has to be speeding up or slowing down. Accelerating just means that v is changing. So here to here, from time 1 to 2, you could write it like that if you want to, or you could just write out the words 1 to 2, that's fine, and also from 3 to 4.5. What is the acceleration? So we know that acceleration is the slope of v versus t. So that should be easy enough to find. Rise 3, run 1. Remember, you can't just count boxes. You got to pay attention to the scale. So that's 3 over 1. The acceleration here is 3 meters per second squared. And the acceleration here, this is a rise of 3, run of 1.5, and it's negative, so this is negative 2. All right, what can you conclude about the forces acting on it? Well, we know from Unit 4 that if forces are balanced, that means that you're at a constant velocity or at rest. If the forces are balanced, you're at constant velocity or at rest. And so that must mean that if you're accelerating, the forces are not balanced. So what can we conclude about the forces acting on the object between 0 and 1? 0 and 1, we are at rest. The velocity is 0. So they are balanced. What can you conclude about the forces between 1 and 2? They must be unbalanced. And since the acceleration is positive in the positive direction, it must be the direction of the imbalance, like which direction is there extra force in. There must be extra, I'm going to say extra for now, force or unbalanced force in the positive direction. What can you conclude about the forces acting on the object between 2 and 3? They're balanced because we are going at a constant velocity of 3. If there was any imbalance, then that would be changing the velocity. So that's balanced forces. And are there any instances where you can conclude that there are no forces acting on the object? No. All that we can say from this is there must be balanced, 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 unbalanced, and unbalanced. It's possible that there could be no forces at all here or no forces at all here, because if you have absolutely no force acting on something, well, that's balanced, right? But we can't conclude that there are no forces. We can just say that they're balanced. So if not, why not? So I'll say we only know that forces are balanced. And when we say that, we only know that the forces are balanced in those 3 intervals. All right. During what time intervals are the forces balanced? We kind of answered these already. So for balanced forces, we're talking about 0 to 1, 2 to 3, and 4.5 to 5. And then unbalanced from 1 to 2 and 3 to 4.5. When there's an unbalanced force acting on the object in the when is there an unbalanced force in the positive direction, in the forward direction? That is, we already talked about that here, from 1 to 2, because the acceleration is positive. If the acceleration is positive, if the velocity is changing in the positive direction, that must be, if you think about broom ball, it must be like tapping, the extra force must be in that same direction. When is there an unbalanced force in the backward direction? That's from 3 to 4.5, because the tapping, the acceleration, is in the negative direction. This is still moving forward. This is like the bowling ball coming into the coming into the end box, right? At the end, it's moving forward, but you have to tap on it backwards to get it to slow down. That's what's happening here. When is the amount of imbalance of the forces the greatest? Well, let's see. If we think that the amount of unbalanced force has to do with how much the velocity is changing or how big the acceleration is, then the bigger the acceleration, the more unbalanced force there is. That would be a very reasonable thing for us to think at this point. So from time 1 to 2, because this is the greatest acceleration. And we didn't care about signs there. If this was like a really big negative number, we wouldn't say, oh, well, this one's positive, so that's big. It's just the size of the number. If this had been like -4, then this would be the biggest unbalanced force. All right, there you go.